Right now, you are sitting inside a structure so large that light itself needs 20,000 years to travel from one end to the other. It is not the Milky Way. It is not a galaxy cluster. It is something most people have never even thought about. It is the spiral arm you live in. The Orion Arm is the local region of the Milky Way that contains our Sun, our planets, every star you have ever seen with your naked eyes. And it stretches across distances so vast that our entire solar system is barely a speck buried inside it. Scientists once dismissed it as a minor spur. New evidence says they were wrong. The arm is enormous, and we are lost inside it. If you enjoy having your sense of scale completely dismantled, do me a favour and hit that like button and subscribe. It really helps the channel grow and lets me keep making these deep dives into the cosmos. Now, settle in and get yourself comfortable. Let's begin. Ask someone where they live in the universe, and they will probably say Earth. Push them further, and they might say the solar system. Push harder, and they will eventually say the Milky Way. That answer feels complete. It sounds like it covers the full picture. Earth, solar system, Milky Way. 3 steps from your front door to the cosmos. Done. But that answer skips something enormous. Between the solar system and the full Milky Way sits a structure so vast that most people have never seriously thought about it. A structure large enough to contain every star you have ever seen in the night sky. A structure that stretches at least 20,000 light-years from end to end and spans roughly 3,500 light-years across. A structure that holds billions of stars, massive clouds of gas and dust, stellar nurseries where new suns ignite, and the scattered remnants of stars that died before our planet even existed. That structure is the Orion Arm. It is the spiral arm of the Milky Way where our solar system actually sits, not the galaxy as a whole. Not some vague region labelled near the centre or out on the edge. A specific, physical, mappable piece of galactic architecture with defined boundaries, a measurable width, a traceable length, and an internal structure complex enough that scientists have spent decades trying to understand it from the inside. And the strange part is how invisible it feels. The Orion Arm does not announce itself when you look up at the sky. You cannot point to it the way you can point to the moon or a bright planet. You cannot see its edges. You cannot sense its shape. You are inside it right now, have been your entire life, and will be for as long as humanity exists on this planet. It surrounds you completely. Every direction you look through the night sky, you are looking through some portion of the Orion Arm's gas and stars and dust. You are embedded in it the way a single cell is embedded inside an organ. The cell cannot see the organ. It does not know the organ's shape. It only knows its immediate surroundings. That is exactly the problem astronomers have faced for over a century. We live inside a spiral arm of a galaxy, and for most of human history, we had no idea the arm was even there. The Milky Way is a barred spiral galaxy. From above, if you could somehow hover 100,000 light-years overhead and look down, you would see a flattened disk of stars and gas, organized into sweeping curved arms radiating outward from a central bar-shaped core. The galaxy contains somewhere between 200 billion and 400 billion stars. It spans roughly 100,000 light-years from edge to edge, possibly more depending on how you define the faint outer regions. It rotates. It has structure. And within that structure, the stars and gas are not spread evenly. They concentrate along arms. The Milky Way has 2 confirmed major spiral arms, the Perseus Arm, which lies farther from the galactic center than we are, and the Scutum Centaurus Arm, which wraps around closer to the core. There are also several minor or intermediate arms, and the picture keeps getting revised as better data arrives. The galaxy's spiral architecture is one of the hardest things in astronomy to pin down, precisely because we are sitting inside the disk, trying to map a pattern we cannot step outside of to see. The Orion Arm sits between 2 of these larger structures. On the side closer to the galactic center lies the Sagittarius Arm, sometimes called the Carina-Sagittarius Arm. On the side farther from the center lies the Perseus Arm, one of the galaxy's 2 dominant spiral features. The Orion Arm bridges the gap between them, running roughly parallel to both, slightly diagonal, stretching from the direction of the constellation Cygnus on one end toward the direction of the constellation Carina on the other. For a long time, astronomers treated it as barely worth mentioning. The standard picture of the Milky Way labelled it as a spur, a small offshoot connecting bigger arms. Galaxy diagrams drew it as a minor feature. Textbooks described it almost apologetically. Just a local spur, a minor bridge, nothing compared to the real arms. That turned out to be wrong, but we will get to why in a moment. First, you need to understand where you actually are inside this thing. The solar system sits near the inner rim of the Orion Arm, not at the centre, not at the outer edge, close to the side that faces the galactic core, roughly halfway along the arm's total length. Our Sun orbits the centre of the Milky Way at a distance of approximately 26,000 light-years, placing us roughly halfway from the galactic centre to the disk's outer edge. We are not in the bustling downtown core of the galaxy. We are more like a quiet suburb, far removed from the intense radiation and gravitational chaos near the central bar and the supermassive black hole that sits at the heart of everything. From our position, the nearest edge of the Orion Arm's inner boundary is only a few hundred light-years away. The outer edge of the arm lies roughly 3,000 light-years in the opposite direction. If you could somehow see the arm in cross-section, our Sun would appear near one wall of a wide corridor of stars and gas, slightly off-centre, tucked into a relatively thin region of the arm's overall width. But even that description understates the situation, because the solar system is not just near the inner rim, it is inside a specific cavity within the arm called the local bubble. The local bubble is a region of space approximately 1,000 light-years across, where the density of interstellar gas is dramatically lower than the surrounding material. It was carved out roughly 14 million years ago by a series of supernova explosions from massive stars in the nearby Scorpius-Centaurus stellar association. Those explosions blasted away the local gas and dust, creating a hot, diffuse cavity that our solar system now drifts through. The interior of the bubble reaches temperatures around 1 million degrees Kelvin, but the gas is so thin that individual hydrogen atoms can be separated by distances measured in miles. The bubble is not a void in the ordinary sense. It is more like a region where the interstellar medium has been heated and thinned to near irrelevance. Think of it this way. The Orion Arm is like a vast forest, stretching thousands of light-years in every direction. Dense clouds of molecular gas form the thickest groves. Bright young stars blaze in clearings where the canopy has been blown open by stellar winds and explosions. And the local bubble is a small meadow within that forest, a pocket of relative emptiness where the trees thin out and the view opens up. Our solar system sits in that meadow. We can see the surrounding forest from where we stand, but the forest extends so far in every direction that its true boundaries vanish beyond what we can observe. That meadow, the local bubble, is 1,000 light-years wide. It sounds enormous. By any human standard, it is enormous. Light takes 1,000 years to cross it. If you could drive a car at highway speed across the local bubble, the journey would take roughly 11 billion years, far longer than the current age of the universe. The local bubble is incomprehensibly vast by the measure of human experience, and it is a tiny clearing inside the Orion Arm. The arm itself is roughly 3.5 times wider than the local bubble and at least 20 times longer. The bubble occupies a small fraction of the arm's total volume. You could fit dozens of local bubbles side by side across the arm's width and hundreds along its length. The cavity we call home, the region of space that contains every star visible to the naked eye from Earth, every constellation humans have ever named, every nearby stellar system we have ever studied in detail, is a small pocket inside a much larger galactic feature that most people have never seriously considered. This is where the first jolt of scale hits. Everything familiar in the night sky lives inside the Orion Arm. Sirius, the brightest star in our sky, sits about 8.5 light-years away. It is inside the arm. Vega, the bright blue star almost directly overhead in northern summer skies, lies about 25 light-years away. Inside the arm. Proxima Centauri, the nearest known star to our Sun at just over 4 light-years distant, is obviously inside the arm. So is every star in the Big Dipper, every star in Orion's belt, every star in Cassiopeia. Every single point of light you can resolve with your unaided eyes on even the clearest, darkest night belongs to the Orion Arm. The stars that form the constellation Orion itself are actually scattered across a wide range of distances within the arm. Betelgeuse, the red supergiant marking Orion's shoulder, sits roughly 700 light-years from Earth. Rigel, the blue supergiant at Orion's foot, lies about 860 light-years away. The three stars of the belt range from roughly 800 to over 1,000 light-years distant. All of them are inside the Orion Arm. All of them are part of the same galactic structure that holds our Sun. They are not close neighbours in any meaningful sense. Some of them are separated from us by distances that light takes centuries to cross. But on the scale of the arm itself, they are practically next door. They are all embedded in the same local stretch of the same spiral feature. And this is what most people miss entirely. When you look up at the night sky and see thousands of individual stars scattered across the darkness, you are not seeing the Milky Way in general. You are seeing the inside of the Orion Arm, the band of soft light that stretches across the sky on clear dark nights. The thing we casually call the Milky Way is the combined glow of billions of distant stars concentrated in the galactic disk. But the individual bright stars you can pick out with your eyes are almost entirely local. They are your neighbours within the arm. The night sky is not a window onto the galaxy. It is a view from inside one specific piece of it. This is the first clue that the Orion Arm is not a minor feature. It is large enough to contain every object that has ever felt close and familiar in the human sky. Now consider what else is in there. The Orion Nebula, one of the most photographed objects in all of astronomy, sits roughly 1,340 light-years from Earth. It is a massive stellar nursery where new stars are actively forming right now, illuminated by a cluster of hot young stars called the trapezium at its core. The nebula spans about 24 light-years across and contains enough gas and dust to form thousands of new stellar systems. It is one of the nearest large star-forming regions to our planet, and it is inside the Orion Arm. The Cygnus X region, one of the richest star-forming complexes in the entire Milky Way, lies roughly 4,600 light-years away in the direction of the constellation Cygnus. It contains some of the most massive and luminous stars known, embedded in enormous clouds of molecular hydrogen that stretch across hundreds of light-years. For years, the distance to Cygnus X was uncertain, and some astronomers believed it might belong to the more distant Perseus Arm. Precise radio measurements revealed the truth. Cygnus X is inside the Orion Arm. It belongs to our structure, the Taurus molecular cloud, a quieter but closer region of active star formation, sits about 440 light-years away. The Rho Ophiuchi cloud complex, another stellar nursery glowing with infrared light from embedded young stars, lies roughly 460 light-years distant. The Vela molecular ridge, a chain of dense gas clouds where stars are being born across a stretch of several hundred light-years, lives inside the arm. The Cepheus star-forming region is inside the arm. The North America Nebula, a striking cloud of ionized hydrogen roughly 1,600 light-years away that gets its name from its shape, resembling the continent, is inside the arm. All of these objects, every one of them, exist within the same galactic structure that holds our Sun. They are not scattered randomly through the Milky Way. They trace the internal anatomy of the Orion Arm, marking places where gas has piled up densely enough for gravity to win its slow battle against thermal pressure and ignite new generations of stars. And here is what that means in practical terms. The Orion Arm is not an empty corridor of space. It is alive. It is one of the most active star-forming environments in our region of the galaxy. Massive stars are being born inside it right now, collapsing out of dense molecular cores that have been accumulating material for millions of years. Other massive stars are approaching the ends of their lives, swelling into red supergiants or blue hypergiants that will eventually detonate as supernovae, seeding the arm with heavy elements and triggering new waves of star formation in the surrounding gas. Some of the most energetic events in our galactic neighbourhood, supernova explosions, the formation of neutron stars and stellar mass black holes, the violent winds of young blue giants carving cavities in the interstellar medium, all of this is happening within the Orion Arm, continuously, right now as you listen to this, and our Sun just drifts through it. One quiet, middle-aged yellow star among billions, carrying its small family of planets along for a ride that has already lasted 4.5 billion years. This brings us to the question that sits underneath everything we have discussed so far. If the Orion Arm is this large, this active, this full of stars and gas and violent stellar processes, why does it feel like a footnote? Why does every popular description of our cosmic address jump straight from the solar system to the Milky Way as if nothing important exists in between? Part of the answer is psychological. Humans are not wired to think about structures they are inside of. You do not spend your day thinking about the atmosphere. You do not constantly remind yourself that you are standing on a tectonic plate. You do not feel the rotation of the Earth beneath your feet. These things are too big, too constant, too surrounding to register in ordinary awareness. The Orion Arm is the same kind of invisible. It is not hidden because it is far away. It is hidden because it is everywhere around you. You cannot see its shape because you are part of it. You cannot sense its edges because they are thousands of light years away in every direction. It does not feel like a thing you are inside because your entire frame of reference, every star and cloud and nebula you have ever observed, exists within it. Part of the answer is also historical. For decades, astronomers classified the Orion Arm as a minor spur, a small, unimpressive bridge between the real spiral arms. Galaxy maps showed it as a stubby little feature, barely worth naming. The Sagittarius Arm and the Perseus Arm were the important structures. The Orion Arm was just a local wrinkle in the disk. That classification shaped how the public understood it, how textbooks presented it, and how even scientists talked about it in casual descriptions of galactic structure. Minor spur, local spur, Orion spur. The vocabulary itself carried a dismissal built into it, but that classification was based on incomplete data. Astronomers were measuring the arm using only the stars and gas clouds they could see from inside it, which is like trying to measure the full length of a hallway while standing in the middle with the lights off and a flashlight that only reaches 10 feet in front of you. They could see nearby features clearly. They could detect bright, massive stars at moderate distances, but the full extent of the arm remained hidden behind curtains of interstellar dust that block visible light, and behind the fundamental difficulty of measuring accurate distances to objects embedded in the same structure you are trying to map. It took a revolution in measurement technology to reveal what the Orion Arm actually is. Radio telescopes that could see through dust. Space missions that could track the precise positions and motions of over 1 billion stars. Techniques that could measure distances to individual star-forming regions with accuracies that previous generations of astronomers could only dream about. When those measurements finally came in, the Orion Arm refused to stay small. The first major surprise arrived in 2013, when a team led by Ye Shu at the Purple Mountain Observatory in China used very long baseline radio interferometry to measure precise distances to bright maser sources, natural microwave beacons associated with regions of massive star formation deep inside molecular clouds. These masers are produced when clouds of gas containing trace molecules like water and methanol amplify microwave radiation into intense, narrow beams that radio telescopes can detect across thousands of light years. By observing these masers from multiple radio telescopes spread across continents and measuring the tiny shifts in their apparent positions as the Earth orbits the Sun, astronomers can calculate their distances through the same parallax method that surveyors use on Earth, only scaled up to galactic proportions. The measurements revealed that the Orion Arm extended much farther than anyone had previously mapped. Stars and gas clouds that had long been assumed to belong to the more distant Perseus Arm turned out to be part of the Orion Arm instead. The arm was not a short, stubby spur. It stretched far enough and showed enough internal structure that the team concluded it might be a branch of the Perseus Arm, or possibly an independent arm segment in its own right. The 2013 paper was the first crack in the old picture, the first serious evidence that our local spiral feature was being dramatically underestimated. In 2016, the same research group published follow-up results that pushed the arm's known length to at least 20,000 light-years. They identified and measured 8 new maser sources within the Orion Arm, and found that the arm's pitch angle, the tilt of its spiral curve relative to circles centered on the galactic core, and its rate of star formation were both comparable to those of the galaxy's major spiral arms like Sagittarius and Perseus. the Orion Arm was not a minor feature. It was, in the words of the researchers, reasonably described as the fifth major structural feature of the Milky Way. Then the Gaia spacecraft entered the picture and changed everything again. Launched by the European Space Agency in 2013, Gaia spent over 11 years scanning the sky and measuring the precise positions, distances, and motions of nearly 2 billion stars before completing its observation phase in January of 2025. Its data releases transformed the study of galactic structure in ways that no single ground-based survey could match. Multiple independent research teams used Gaia data to trace the distribution of young stars, open clusters, and interstellar dust across the Milky Way disk. Their results converged on the same conclusion. A team led by Ye Shu used Gaia early data to estimate the local arm's length at over 25,000 light-years, consistent with the Maser parallax measurements. A separate team led by Eloisa Poggio at the University of the Côte d'Azur in France used Gaia data to map hundreds of thousands of young blue stars and confirmed the same extended picture. The Orion Arm, once dismissed as a minor spur, was revealing itself as a substantial spiral structure with properties that rival the galaxy's traditionally recognized major arms. Gaia even showed that the Milky Way's spiral arms in general may be less sharply defined than older models assumed, with the boundaries between arms appearing more ragged and complex than the elegant textbook spirals suggested. These discoveries did not just change a number on a chart, they changed what the Orion Arm means. It went from being a minor background feature, something you glance past on a galaxy diagram on the way, to more impressive structures, to being a genuine galactic structure. A full-scale spiral arm segment containing billions of stars, active star-forming regions rivaling anything in the Perseus or Sagittarius arms, and an internal architecture complex enough that scientists are still mapping its details today. And our solar system is buried inside it, not perched neatly on the outside, not hovering near a conveniently labelled dot on a diagram. Embedded within the arm's structure, surrounded by its gas and dust and stars in every direction, sitting in a 1,000 light-year clearing that barely registers against the arm's full scale. The textbooks that called it a minor spur were not lying. They were measuring a shadow. They were seeing only the nearest, brightest pieces of a structure that extends far beyond what their instruments could reach. The Orion Arm is not minor. It is not a footnote. It is the galactic structure that contains everything humans have ever called home, and its true scale is far more disturbing than even this revised picture suggests. What comes next will make the arm feel less like a neighborhood and more like an ocean with no visible shore. The solar system feels big. It should. It took the Voyager 1 spacecraft, traveling at roughly 17 kilometers per second, over 35 years, just to reach the boundary where the solar wind gives way to interstellar space. The distance from the Sun to Neptune, the outermost major planet, is approximately 4.5 billion kilometers. If you drove that distance at highway speed without stopping, the trip would take over 5,000 years. The solar system, measured out to the theoretical outer edge of the Oort cloud, may extend as far as 2 light-years from the Sun in every direction. That is an enormous volume of space by any standard a human being can personally experience. Now, place that volume inside the Orion Arm. The arm is roughly 3,500 light-years wide. The solar system's full extent, out to the most distant hypothetical reaches of the Oort cloud, spans about 4 light-years across. That means you could line up nearly 900 solar systems side by side across just the width of the Orion Arm. Not its length, its width, the narrow dimension. And 900 is a generous estimate, because most of the solar system's meaningful structure, the region containing all 8 planets, fits within a diameter of roughly 10 light-hours, which is so small relative to the arm's width that it vanishes entirely from any map drawn at galactic scale. Go further. The Orion Arm stretches at least 20,000 light-years from end to end. Some measurements push it closer to 25,000. At that scale, the solar system does not merely shrink, it ceases to be representable. If you drew the Orion Arm as a rectangle on a piece of paper, say 30 centimeters long by 5 centimeters wide, the solar system would not be a dot. It would not be a pixel. It would be smaller than a single atom of ink on the page. You could not mark it even if you tried. This is the first real confrontation with what it means to live inside this structure. The solar system is not small in any way a human can intuitively understand. It is simply operating at the wrong scale to register against the arm that contains it. Let me make this worse. The nearest star to our Sun is Proxima Centauri, just over 4 light-years away. That distance is already so extreme that no human technology can cross it in a single lifetime. The fastest spacecraft humanity has ever launched would need roughly 70,000 years to reach it. And yet, that distance, the gap between our Sun and the closest neighbouring star, amounts to approximately 1/5000th of the arm's length. Imagine standing on one end of a runway 5 kilometres long. The distance to Proxima Centauri, the gap that currently represents the absolute frontier of human ambition in interstellar travel, would be a single step. 1 metre on a 5-kilometre path, that is how the nearest star compares to the length of the Orion Arm. Extend the picture to other well-known nearby stars. Sirius, the brightest star in the sky, sits 8.5 light-years away. On the same 5-kilometre scale, that is roughly 2 steps. Vega, 25 light-years distant, is about 12 steps. Arcturus, one of the most luminous stars in the northern sky, lies 37 light-years away, 18 steps. All of these stars, the brightest and most familiar objects in the human sky, represent distances so trivial relative to the Orion Arm that they barely qualify as motion along the arm's length. And yet, these distances already defeat us. We cannot cross them. We cannot communicate across them in any reasonable time frame. The fastest possible signal, a beam of light, takes 4 years to reach Proxima Centauri, 8.5 years to reach Sirius, 25 to reach Vega. Each of these trips is already beyond the horizon of practical human activity, and each of them covers a distance so tiny relative to the arm that it rounds to nothing. Consider how Voyager 1 fits into this picture. It launched in 1977. It has been flying away from Earth continuously for nearly 5 decades. It is the most distant human-made object in existence, and in all that time, travelling at 17 kilometers per second, it has covered approximately 0.0027 light-years. Compare that to the arm's width of 3,500 light-years. Voyager's entire journey so far amounts to less than 1/millionth of the distance across the narrow dimension of the structure we live in. If the Orion Arm's width were the distance from New York to London, Voyager 1 would not have made it out of the departure terminal. About 4 meters of pavement, that is the fastest object humanity has ever flung into the void, and it has not even begun to matter against the arm's scale. This is where the psychological compression begins. The human mind defaults to treating nearby stars as though they represent the scale of our galactic environment. We say the nearest star is 4 light-years away, and that feels like the edge of our local world. We think of stars within a few dozen light-years as our neighbourhood, but our neighbourhood is a pinprick. The arm extends thousands of times farther than the distances we think of as vast. The comfortable language of nearby and far away collapses completely when you try to apply it inside a structure this large. Consider what happens when you zoom out just a little more. Our Sun belongs to no star cluster. It drifts through the arm as a field star, unattached to any gravitationally bound group. But other stars in the Orion Arm do belong to clusters. The Pleiades, that small bright cluster visible in winter skies, sits roughly 440 light-years away. The Hyades, an older and closer cluster, lies about 150 light-years from Earth. These clusters contain hundreds of stars each, born together from the same collapsing gas cloud millions of years ago, still moving through space as a coherent group. These clusters are inside the arm. They are specks inside it. The Pleiades, a cluster you can see with your unaided eyes and that humans have used for navigation and storytelling for thousands of years, occupies a volume roughly 43 light-years across. That is about 1% of the arm's width. 1%, the entire cluster, all its stars and gas and gravitational influence, amounts to a tiny clot of material embedded in one small region of the arm's much larger body. And here is where the arm begins, revealing just how much it contains. In 2020, a team of astronomers led by João W. Alves at the University of Vienna, Catherine Zucker at the Harvard Smithsonian Center for Astrophysics, and Alyssa Goodman at Harvard made a discovery that redrew the interior map of the Orion Arm in one stroke. Using three-dimensional dust mapping techniques powered by precise distance measurements from the Gaia spacecraft, they identified a structure no one had seen before, a gigantic, undulating chain of dense gas clouds stretching roughly 9,000 light-years through the arm's interior, connecting many of the most famous star-forming regions in our galactic neighborhood into a single, coherent, wave-shaped feature. They named it the Radcliffe Wave, after the Harvard Radcliffe Institute where the discovery was made. The Radcliffe Wave threads through the Orion Arm like a spine. It connects the Orion molecular cloud complex to the Taurus clouds, the Perseus clouds, the Cepheus star-forming region, the North American Nebula, and the Cygnus star-forming complexes into one continuous sinusoidal ribbon of gas. The wave oscillates above and below the galactic plane, rising as high as 500 light-years above the disk midplane in some places and dipping below it in others. Its closest point passes within roughly 500 light-years of our Sun. It is, in a very real sense, the backbone of the nearest spiral arm. For years, astronomers had studied these star-forming regions individually. The Orion Nebula was one object. Taurus was another. Perseus was a third. They were treated as separate features, catalogued independently, analysed in isolation. The Radcliffe Wave revealed that they are all part of a single connected structure, a chain of stellar nurseries strung along the arm like beads on a wire, linked by gas and dust and the underlying gravitational field of the spiral arm itself. And in February of 2024, the story deepened. A team led by Ralph Kony-Etzker at Harvard published a paper in Nature showing that the Radcliffe Wave is not just shaped like a wave, it moves like one. Using updated Gaia data to track the three-dimensional motions of young star clusters born within the wave's gas clouds, the researchers demonstrated that the entire 9,000 light-year structure is oscillating. It undulates up and down through the galactic plane over time, driven by the gravitational pull of the Milky Way's disk. The wave ripples through space the way a traveling wave moves through a stadium full of fans, each section rising and falling in sequence as the disturbance propagates along the structure's length. No one knows what caused the wave. No one knows what initially displaced the gas from the galactic midplane to set the oscillation in motion. Some researchers have speculated about a past collision with a massive gas cloud or a dark matter substructure passing through the disk. Whatever the trigger, the result is a dynamic, living feature inside the Orion Arm, a structure that breathes and moves on timescales of millions of years, giving birth to new stars along its entire length as it ripples through the galactic plane. And here is something that makes the Radcliffe Wave feel uncomfortably close to home. In early 2025, a team led by Mark O'Neill and colleagues published a study in the journal Astronomy and Astrophysics, showing that the solar system did not merely drift near the Radcliffe Wave, it passed directly through it. Sometime during the Middle Miocene epoch, roughly 12 to 15 million years ago, our Sun's orbit through the galaxy carried the entire solar system through the dense gas of the wave's Orion region. The encounter likely lasted several million years, during which the solar system would have been immersed in the denser interstellar environment of a star-forming cloud complex. This was not a gentle brush. The passage would have compressed the heliosphere, the protective bubble of solar wind that surrounds our planetary system, pushing interstellar material closer to the inner solar system than it normally reaches. The researchers suggested that increased dust from this galactic encounter could have penetrated Earth's atmosphere, potentially leaving traces of radioactive isotopes from nearby supernovae in geological sediment layers. The evidence is not yet confirmed, partly because current detectors may not be sensitive enough to pick up the signal, but the implication is striking. The Orion Arm is not just the abstract structure that contains us, it has physically interacted with our planet. Its gas clouds have touched our solar system, its supernovae may have left chemical fingerprints in Earth's rocks. The arm is not a backdrop, it is an environment that has reached down and altered the conditions on the surface of our world. 9,000 light-years. A single connected structure of gas and newborn stars, oscillating through the interior of our spiral arm, and we only discovered it existed in 2020 because we finally had the technology to see it. And we only discovered that we had passed through it in 2025. This is what the Orion Arm contains. Not just scattered stars and isolated nebulae, but enormous coherent structures spanning thousands of light years, hiding in plain sight because we lacked the three-dimensional mapping tools to recognize them. The arm is not a simple corridor of stars. It is a layered, dynamic environment with internal architecture that scientists are still uncovering. The Radcliffe Wave is the most dramatic recent example, but it is not the only large-scale feature inside the arm. The arm contains vast complexes of molecular gas, regions where hydrogen exists not as individual atoms but as molecules packed into cold, dense clouds with temperatures just a few degrees above absolute zero. These molecular clouds are the raw material for star formation. They fill the arm's interior in enormous concentrations, some of them spanning hundreds of light years across and containing enough mass to form thousands of stars. The Orion Molecular Cloud Complex, the parent structure of the Orion Nebula, stretches roughly 240 light-years from end to end and contains roughly 200,000 times the mass of our Sun in gas and dust. Stars are forming throughout this complex right now, collapsing out of dense cores buried inside the cloud's darkest, coldest regions. The Orion Nebula itself is just the most visible piece of a much larger system. The Cygnus X complex, which lies near one end of the Orion Arm in the direction of the constellation Cygnus, is even more massive. It contains millions of solar masses of molecular gas spread across a region several hundred light-years wide. It is one of the most prolific star-forming regions in the entire galaxy. Some of the most massive stars known, blue supergiants burning through their fuel at rates millions of times greater than our Sun, were born inside Cygnus X within the last few million years. This region alone has shaped the interstellar environment of the Orion Arm's far end through its intense radiation, powerful stellar winds, and the supernova explosions of its earliest and most massive members. Between these major complexes, the arm is threaded with diffuse interstellar gas, streams of neutral hydrogen atoms that emit faint radio radiation at a wavelength of 21 centimeters. This gas traces the arm's overall shape at the largest scales. It is one of the primary tools astronomers use to map spiral structure. Because neutral hydrogen is abundant and its radio emission passes through the dust that blocks visible light. Radio surveys of the 21 centimeter line have been mapping the Milky Way's arms since the 1950s, and they remain essential for understanding the arm's full extent. Dust fills the arm as well. Microscopic grains of carbon and silicate, produced in the outer layers of dying stars and scattered through the interstellar medium, accumulate in the densest parts of the arm. These grains absorb and scatter visible light, creating the dark lanes and patches you can see in long-exposure photographs of the Milky Way. The dust is both a nuisance and a tool. It blocks our view of distant stars and structures, making the arm harder to map in visible light. But it also glows in infrared, and by mapping its thermal emission, astronomers can trace the arm's dense regions even where optical telescopes see nothing. This brings us to a realization that changes how the arm should feel. The Orion Arm is not mostly empty space dotted with occasional stars. By galactic standards, it is a dense, structured environment. The average density of the interstellar medium within a spiral arm is several times higher than the density between arms. Gas piles up along the arm's length, compressed by the spiral density wave that maintains the arm's overall shape. Stars form preferentially within arms because of this compression. The brightest, hottest, most massive stars in the galaxy, the O-type and B-type giants that burn blue-white and live only a few million years, are found almost exclusively within spiral arms. They are born inside the arm's dense gas and die before they can drift away. These massive stars are the lighthouses of galactic structure. They are so bright that they can be seen from enormous distances, and their concentration within spiral arms is one of the primary ways astronomers identify arm locations in other galaxies. When you look at a photograph of a distant spiral galaxy and see its arms traced in brilliant blue-white light, you are seeing the collective glow of O-type and B-type stars, the same kinds of stars that populate the Orion Arm and trace its structure. Within our arm, these massive stars cluster into groupings called OB associations, loose collections of young, bright stars that form together from the same giant molecular cloud. The Orion OB1 association, centered on the constellation Orion, is one of the nearest and best studied. It contains several subgroups of stars spanning ages from roughly 12 million years down to less than 1 million years, tracing multiple generations of star formation within the same region of the arm. The Scorpius-Centaurus association, which lies closer to the Sun, is another major OB grouping within the arm. It was the supernova explosions of massive stars in this association that carved out the local bubble roughly 14 million years ago. These associations are enormous. Scorpius-Centaurus spans roughly 400 light-years across. Orion OB, one stretches across a similar distance. Each one is a significant substructure within the arm, a region where dozens of massive stars have formed and exploded over millions of years, reshaping the surrounding gas and triggering cascading waves of new star formation. And yet, even the largest of these associations is small compared to the arm. 400 light-years is about 11% of the arm's width and barely 2% of its length. The associations are significant features, but they are features within a much larger feature. They are rooms inside a building that stretches far beyond what any single room can reveal, but the massive O-type and B-type stars are only the brightest inhabitants. They are not the most numerous. For every blazing blue giant in the arm, there are thousands upon thousands of smaller, dimmer stars that no human eye will ever see. Red dwarfs, the smallest and coolest hydrogen-burning stars, make up roughly 70% of all stars in the Milky Way. They are so faint that even the nearest one, Proxima Centauri, is invisible to the naked eye despite being the closest star to our Sun. The Orion Arm contains billions of these dim red embers, scattered throughout its volume, burning steadily, many of them likely orbited by planets, and almost all of them completely unknown to us individually. Think about what that means. We have catalogued the bright, hot stars within a few thousand light years. We have identified many of the clusters and associations and nebulae, but the vast majority of the arm's stellar population, the ordinary, quiet, long-lived stars that make up the bulk of its mass, have never been individually observed beyond the nearest few hundred light years. They exist in numbers so large that even modern surveys can only sample a fraction. Gaia catalogued nearly 2 billion sources across the entire sky, and that extraordinary number still represents only a small percentage of the total stellar population of the Orion Arm alone. Current estimates suggest the arm contains somewhere in the range of several billion stars along its full extent. Each of those stars is a furnace. Each one has a gravitational domain. Many of them have planetary systems. Some fraction of those planetary systems may include rocky worlds in zones where liquid water could persist on the surface. We do not know how many. We cannot see them. They are too distant and too faint. But the statistical certainty is that the arm contains vast numbers of worlds we have never detected, orbiting stars we have never named, scattered throughout a volume of space we have only partially mapped. A single planetary system, even a rich one like our own with 8 planets and hundreds of moons, is like a pebble tossed into a lake the size of a continent. It exists, it is real, and it is utterly lost in the scale of the water around it. And this is where the scale problem becomes genuinely difficult to hold in the mind. Every object we have discussed, the Radcliffe Wave, the Cygnus X complex, the Orion molecular cloud, the Scorpius-Centaurus association, the local bubble itself, is a major, well-studied, scientifically important structure. Each one represents decades or centuries of astronomical research. Each one fills journals and conferences and doctoral dissertations. And each one is a subcomponent of the Orion Arm, a piece of the arm's internal anatomy, a feature within a structure that itself sits inside a much larger galaxy. The arm contains all of them simultaneously. It has room for all of them simultaneously, and it has room for vastly more that we have not yet catalogued or even detected. Let me try to make the volume concrete. The Orion Arm, approximated very roughly as a flattened rectangular slab about 20,000 light-years long, 3,500 light-years wide, and 1,000 light-years thick, encloses a volume of roughly 70 billion cubic light-years. That number is already meaningless in human terms, but compare it to the solar system, the region of space dominated by our sun's gravity, out to the estimated outer edge of the Oort cloud, fills a sphere roughly 4 light-years in diameter. Its volume is about 33.5 cubic light-years. The Orion Arm's volume is approximately 2 billion times larger than the volume of our solar system. If the arm were a football field, the solar system would not be a grain of sand sitting on the turf. It would be something far smaller than a grain of sand, something closer to a single bacterium riding a dust mote drifting through a cathedral. 2 billion times. That ratio is the distance between the scale of everything you know and the scale of the galactic structure that contains it. The solar system, with all its planets and moons and comets and asteroids, and the vast empty stretches between them, occupies less than 1 2-billionth of the arm's volume. And the arm is not even the galaxy. It is one structural component of the galaxy. It is a single piece of the Milky Way's spiral architecture. The galaxy itself is incomparably larger, and beyond the galaxy lies the local group, and beyond that the Virgo supercluster, and beyond that the Laniakea supercluster, and beyond that the observable universe stretching 93 billion light-years across. But we are not talking about any of that. We are talking only about the arm, the local arm, the one we live in, the one that most people have never heard of or have glanced at on a diagram and immediately forgotten. This is what makes the Orion Arm so disorienting. It is not far away. It is not exotic. It is not on the other side of the galaxy or at the edge of the observable universe. It is right here. It is the immediate environment, and it is so large that our entire solar system, the only home we have ever known, the only world we have ever touched, disappears into it like a raindrop falling into the Atlantic Ocean. Not visible on the surface, not detectable from above, simply absorbed into something vastly, overwhelmingly larger. This is the structure that astronomers once called a minor spur. This is the feature that galaxy diagrams drew as a small, unimportant stub, 20,000 light-years long, 3,500 light-years wide. Containing the Radcliffe Wave, the Cygnus X complex, the Orion molecular cloud, the Scorpius-Centaurus association, the local bubble, billions of individual stars, and enough molecular gas to keep forming new stars for millions of years to come. And we have mapped only a fraction of it. The regions closest to the Sun are well studied. The features within a few thousand light-years have been catalogued and measured with increasing precision thanks to Gaia and modern radio surveys. But the arm extends far beyond our current high-precision mapping. Its far end, stretching toward the constellation Carina and beyond, remains poorly constrained. Dust blocks our view. Distance measurements become less reliable. Entire star-forming complexes may exist in the arm's more distant reaches that we have not yet identified. The arm we think we know may be even larger, even more complex, even more populated than current data reveals. This is the Orion Arm as it actually exists. Not a label on a chart, not a background detail. A galactic-scale structure that dwarfs everything inside it by factors that ordinary language cannot convey, and we have only known its true scale for about a decade. But knowing that it is large raises an even harder question. How do you map something this enormous when you are trapped inside it and cannot step outside to see its shape? The answer involves some of the most ingenious measurement techniques in all of science, and the story of how they revealed the arm from within is as remarkable as the arm itself. There is a fundamental absurdity at the heart of everything we know about the Orion Arm. We have never seen it. No human has ever looked at the Orion Arm from the outside. No camera has ever photographed it. No spacecraft has ever climbed high enough above the galactic plane to look back down and trace its spiral curve against the disk of the Milky Way. Every single piece of information we have about the arm, its shape, its width, its length, its internal structure, the position of our sun within it, has been deduced from the inside. We are embedded in the thing we are trying to describe. We have never left it. We never will. Every beautiful illustration you have ever seen of the Milky Way, those sweeping overhead views showing labelled spiral arms curling outward from a bright central bar, is an artist's interpretation built on indirect measurements. No one has ever taken that photograph. The picture exists only because generations of astronomers developed increasingly clever techniques for extracting structural information from a vantage point that should, by rights, make the task nearly impossible. Mapping the Orion Arm from inside the Milky Way is like trying to map a continent from a single fixed point on the ground using only echoes and shadows. You cannot fly above the terrain. You cannot move to a different vantage point. You are stuck in one place, surrounded by the thing you are measuring, and most of it is hidden behind obstacles you cannot see through. The challenge is not merely difficult. It is one of the hardest observational problems in all of astronomy, and the fact that we have solved it as well as we have represents one of the great achievements of modern science. The difficulty begins with dust. Interstellar dust, tiny grains of carbon and silicate scattered throughout the arm's gas, absorbs and scatters visible light. A star 10,000 light-years away might be completely invisible to an optical telescope, not because it is faint, but because the dust between us and the star has absorbed its light entirely. In the densest regions of the arm, where molecular clouds pile up along the spiral structure, dust can block everything behind it for thousands of light-years. The galactic center itself, sitting 26,000 light-years away, is entirely invisible in optical wavelengths. If you pointed the largest optical telescope on Earth directly at the heart of the Milky Way, you would see nothing but dark clouds. This dust is not distributed evenly. It concentrates within the spiral arms, exactly where the stars and gas are densest. The very structures astronomers are trying to map are also the structures that block the view. The Orion Arm's own gas and dust prevent us from seeing its full extent in visible light. We can observe nearby stars and nebulae clearly, but beyond a few thousand light-years, the arm's interior becomes increasingly opaque. Looking along the arm's length, towards Cygnus at one end or Carina at the other, the view is even worse, because the dust accumulates along the entire line of sight, stacking up over enormous distances. This is why the arm was underestimated for so long. Early astronomers mapped what they could see. They counted bright stars, identified nebulae, and measured the positions of the nearest objects. Where the stars thinned out and the dust took over, they assumed the structure ended. The Orion Arm appeared to be a short, stubby feature because the visible evidence ran out after a few thousand light-years in every direction. The arm did not end there. The view ended there. But even with those limitations, there was one extraordinary moment when a single astronomer cut through the confusion and showed, for the first time, that the stars around us traced real spiral structure. In December of 1951, at the 86th meeting of the American Astronomical Society, an astronomer named W.W. Morgan from Yerkes Observatory in Williams Bay, Wisconsin, presented something no one had seen before. He did not show a graph. He did not project a photograph. He built a physical model, a wooden board roughly the size of a tabletop, into which he had driven 25 nails. Atop each nail sat a small white cotton ball. Each ball represented the measured position of an OB association, a grouping of hot, massive, young stars whose distances Morgan and his colleagues had painstakingly calculated using photometric techniques. When the audience looked at the board, the cotton balls were not scattered randomly. They fell into three distinct linear groupings, three parallel bands of bright young stars stretching across the sky. Morgan told the audience they were looking at three spiral arms of the Milky Way. The nearest band, the one passing closest to the Sun, would later be named the Orion Arm. The one farther inward toward the galactic center became the Sagittarius Arm. The one farther outward became the Perseus Arm. The room erupted. Astronomers at the meeting described the moment as electrifying. For the first time in history, someone had demonstrated observational evidence that the Milky Way had spiral arms. The idea had been proposed theoretically for nearly a century, but Morgan's 25 nails, each one placed according to a measured distance, turned a hypothesis into something you could see and touch. It was a crude model, 25 data points for a structure spanning tens of thousands of light-years, but it was the beginning, and the name Orion Arm traces directly back to that wooden board, to those white cotton balls, to a winter night in 1951, when a man with a hammer and a bag of nails showed the world the shape of our galactic neighborhood. The decades that followed would refine Morgan's picture beyond recognition, but the fundamental challenge he faced, measuring the galaxy from inside it, would persist. Breaking through the next barrier required moving beyond visible light entirely. The first great breakthrough came from radio astronomy. In 1951, the same year as Morgan's presentation, astronomers detected the 21-centimeter emission line of neutral hydrogen for the first time. This emission, produced when the spin of an electron in a hydrogen atom spontaneously flips relative to the spin of the proton, generates a photon at a very specific radio frequency. The signal is individually feeble, but hydrogen is the most abundant element in the universe, and the interstellar medium of the Milky Way contains vast quantities of it. The collective emission from billions of hydrogen atoms along any given line of sight produces a radio signal that radio telescopes can detect across the entire galaxy. Critically, radio waves at 21 centimeters pass through interstellar dust as if it were not there. The grains that block visible light are far too small to affect radio wavelengths. A radio telescope tuned to the hydrogen line can see through the arm's dust and detect gas on the far side of the galaxy. For the first time, astronomers had a tool that could map the Milky Way's structure independent of the dust that had blinded optical surveys. Within a few years, radio surveys of the hydrogen line began revealing the Milky Way's spiral architecture. By measuring the Doppler shift of the hydrogen emission at different points in the sky, astronomers could estimate how fast the gas was moving toward or away from Earth. Combining this velocity information with models of galactic rotation, they could estimate the distances to the emitting gas clouds and begin building a map of where gas concentrated throughout the disk. The result was the first rough sketch of the Milky Way's spiral arms, including the earliest identifications of the Sagittarius Arm, the Perseus Arm, and the local feature that would eventually be known as the Orion Arm. But radio mapping of hydrogen had serious limitations. The distance estimates derived from Doppler velocities depended on assumptions about how the galaxy rotates, and those assumptions introduced large uncertainties. Gas clouds at similar velocities but very different distances could be confused with each other. The maps were blurry, ambiguous, and often contradictory. Different research groups produced different spiral arm models depending on which assumptions they used. The Milky Way's structure remained frustratingly uncertain, even after decades of radio surveys. What astronomers really needed were direct distance measurements to objects inside the spiral arms, not velocities reinterpreted through rotation models. Actual distances, measured geometrically, with precisions good enough to place individual objects at specific locations within the galactic disk. This is where masers changed everything. A maser is the microwave equivalent of a laser. It produces an intense, narrow beam of radiation at a specific frequency, amplified by stimulated emission of radiation within a cloud of gas. In the interstellar medium, masers form naturally in regions of massive star formation, where energy from newly forming stars pumps molecules like water, methanol, and silicon monoxide into excited states that produce powerful microwave emission. These natural masers are extraordinarily bright at radio wavelengths. A single maser spot can outshine the sun by factors of billions in its narrow emission frequency. They are visible across the entire galaxy. More importantly, masers are compact. Their emission comes from regions small enough that radio interferometers, arrays of telescopes spread across continental distances, can pinpoint their positions on the sky with extraordinary precision. The technique is called Very Long Baseline Interferometry, or VLBI, and it achieves angular resolutions thousands of times sharper than the best optical telescopes on Earth. By observing a maser source from multiple telescopes spread across a continent and combining the signals, astronomers can measure the position of that maser on the sky with an accuracy of roughly 10 millionths of an arcsecond. That is equivalent to measuring the width of a human hair from a distance of 500 kilometers. This precision enables something remarkable. If you observe a maser at 2 times 6 months apart, the Earth has moved from one side of its orbit around the Sun to the other, a baseline of roughly 300 million kilometers. The maser's apparent position on the sky shifts ever so slightly between the two observations, just as your finger appears to shift against the background when you close one eye and then the other. This shift is called trigonometric parallax, and it is the most direct and reliable method of measuring distance in astronomy. Measure the parallax angle. Calculate the distance. No models required. No assumptions about galactic rotation. Pure geometry. For nearby stars within a few hundred light-years, parallax can be measured with optical telescopes, but for objects thousands of light-years away, the parallax angles become vanishingly small, far too tiny for optical instruments to detect. This is where radio interferometry takes over. The angular precision of VLBI is high enough to measure parallaxes to masers across the entire Milky Way disk. For the first time, astronomers could measure direct geometric distances to star-forming regions embedded deep within the galaxy's spiral arms, thousands or even tens of thousands of light-years away. The Bar and Spiral Structure Legacy Survey, known as BSCEL, was designed to exploit exactly this capability. Led by Mark Reed at the Harvard-Smithsonian Center for Astrophysics and Ye Xu at the Purple Mountain Observatory in China, the project used the Very Long Baseline Array, a network of 10 radio telescopes spanning from Hawaii to the Virgin Islands, to measure trigonometric parallaxes and proper motions of hundreds of masers associated with high-mass star-forming regions throughout the Milky Way. The results were transformative. Each maser parallax pinned down the distance to a specific star-forming region with a typical uncertainty of only 10 to 15%. Plotting these measured positions on a map of the galactic disk revealed the spiral arms directly, not through models or velocity assumptions, but through the actual measured locations of the places where stars are being born. The Perseus arm appeared clearly, traced by maser sources stretching tens of thousands of light-years in a sweeping curve. The Sagittarius arm appeared inward, the Scutum Centaurus arm appeared farther toward the galactic center, and the Orion arm revealed itself as something far larger than the old maps had shown. This is where the 2013 and 2016 results we discussed earlier came from. Ye Xu, Mark Reed, and their collaborators measured maser parallaxes to star-forming regions within the Orion Arm and found sources stretching far beyond the previously assumed boundaries. Regions that had been assigned to the Perseus Arm based on their velocities turned out to be much closer, sitting squarely within the Orion Arm. The arm's measured length grew from the old estimate of roughly 10,000 light-years to at least 20,000, possibly 25,000. The pitch angle of the arm, roughly 10 to 12 degrees, matched the pitch angles of the galaxy's recognized major arms. The density of high-mass star-forming regions within the arm was comparable to that within the Sagittarius and Perseus arms. The Orion Arm was not a spur. It was a legitimate spiral arm segment, with properties indistinguishable from the major arms by every structural measure the researchers examined. The Cygnus X star-forming region, one of the richest in the galaxy, had long been a puzzle. Its location was ambiguous. Velocity-based distance estimates placed it in the Perseus Arm, but the measurements were uncertain. B-cell parallaxes resolved the question definitively. Cygnus X sits at roughly 4,600 light-years from the Sun, placing it solidly within the Orion Arm. This single measurement dramatically extended the arm's known reach towards Cygnus, and confirmed that the arm harbours one of the most prolific star-forming complexes in the entire Milky Way. Then Gaia arrived and multiplied the data by orders of magnitude. The European Space Agency's Gaia spacecraft launched in 2013 with a mission to measure the precise positions, distances, and motions of stars across the Milky Way. Over the course of more than 11 years of continuous observations, ending in January 2025, Gaia catalogued nearly 2 billion sources. It measured parallaxes for over 1 billion stars, providing direct geometric distances to an unprecedented number of objects across the galactic disk. Its angular precision, while less extreme than VLBI for individual sources, was applied to such an enormous number of stars that it revealed galactic structure through sheer statistical power. Gaia's successive data releases reshaped the study of spiral structure. Researchers mapped the distribution of young, bright O-type and B-type stars across the disk, since these massive, short-lived stars are born within spiral arms and die before they can drift far from their birthplaces. The distributions revealed coherent arm-like features stretching across thousands of light-years. The Orion Arm appeared clearly in multiple independent analyses, traced by young stellar populations, open clusters, and regions of enhanced stellar density. A team led by Ye Xu used Gaia's early data release to confirm the arm's extended length, estimating it at more than 25,000 light-years. Independently, Alo, Aisa, Pojo. At the University of the Côte d'Azur and her collaborators used Gaia data to map hundreds of thousands of young blue stars and found the same extended local arm stretching across the disk. A third team confirmed the result, using open cluster distributions. 3 independent groups, using different stellar tracers and different analysis methods, converged on the same conclusion. The Orion Arm is far larger than the old classification allowed. Gaia also contributed something subtler but equally important. Its data revealed that the Milky Way's spiral arms are not the clean, sharply defined features that older models depicted. The arms are ragged. Their edges are not crisp boundaries but gradual transitions where stellar density rises and falls. Spurs, branches, and interarm features complicate the picture. The Cepheus spur, a diagonal structure extending from the Orion Arm toward the Perseus Arm, was identified using Gaia data for O-type and B-type stars. Features like this blur the line between arm and interarm space, making the Milky Way's spiral pattern messier and more complex than the elegant 4-arm or 2-arm diagrams that textbooks favour. This messiness is itself informative. It tells us that the Milky Way's spiral arms are not rigid, permanent structures etched into the galactic disk. They are dynamic features, and understanding what maintains them requires one of the most counterintuitive ideas in galactic astronomy: density wave theory. In the mid-1960s, 2 applied mathematicians at the Massachusetts Institute of Technology, C. Lin and Frank Shu, proposed that spiral arms are not collections of specific stars moving together through the galaxy. Instead, they are patterns. Gravitational patterns that rotate through the disk at their own speed, separate from the speed of the stars and gas that populate them. The arms are zones of compression, regions where the gravitational potential of the rotating pattern squeezes the interstellar material together, increasing its density and triggering star formation. Think of a traffic jam on a highway. The jam itself stays in roughly the same place. Cars enter the jam from behind, slow down, and then eventually pass through the front and speed up again. The cars are not the jam. They are moving through the jam. The jam is a pattern maintained by the conditions on the road, not by any particular set of vehicles. Individual cars enter it, spend time inside it, and leave. Spiral arms work the same way. Stars and gas orbit the galactic center at their own speeds, determined by gravity and their distance from the core. As they move through the disk, they periodically enter a spiral arm, a region of enhanced gravitational potential where everything crowds together. Inside the arm, gas compresses, molecular clouds form, stars ignite. The brightest, most massive stars burn through their fuel and die as supernovae before the material drifts out the other side. The dimmer, longer-lived stars eventually exit the arm and continue their orbits through the lower-density interarm region until they encounter the next arm. This means the Orion Arm is not a permanent home. It is a temporary one. Our Sun is currently inside the arm, but it has not always been, and it will not always remain so. Over the course of its 4.5 billion-year life, the solar system has orbited the galactic center roughly 20 times, and during those orbits it has drifted through different parts of the disk, entering and leaving spiral arms and interarm regions. The arm we call home today is a temporary address on a galactic timescale. In 100 million years, the solar system may have drifted to a different part of the disk entirely. The Orion Arm will still exist as a pattern, but the stars within it will be different stars, having cycled through the compression zone and moved on. The arm persists, its inhabitants rotate through. This makes the Orion Arm even harder to pin down than its size alone suggests. It is not just large, it is transient in its composition. The stars inside it now are not the same stars that were inside it 100 million years ago, and they will not be the same stars 100 million years from now. The arm is a persistent structure populated by a constantly changing set of objects, including our Sun, which happens to be passing through it during the particular epoch in which humanity exists. Beyond mesas and stellar mapping, a third technique has proven essential for understanding the arm's structure: 3-dimensional dust mapping. Interstellar dust absorbs starlight, and the amount of absorption depends on how much dust lies between the star and the observer. By measuring the colours and brightnesses of millions of stars at known distances, astronomers can work backward to calculate how much dust exists at each distance along each line of sight. Stacking these measurements across the sky produces a 3-dimensional map of dust density throughout the nearby galaxy. It was precisely this technique, applied to Gaia distance measurements, combined with photometric surveys, that led to the discovery of the Radcliffe Wave in 2020. The wave had been invisible to previous surveys because no one had the three-dimensional resolution to see that individual star-forming clouds were connected into a single coherent structure. Two-dimensional projections on the sky showed isolated clouds scattered across different constellations. Only when accurate distances placed those clouds into three-dimensional space did the wave-like pattern emerge, linking Orion to Taurus to Perseus to Cepheus to Cygnus in one continuous sinusoidal ribbon. The Radcliffe Wave's discovery was a direct product of the mapping revolution. Without Gaia distances, without three-dimensional dust reconstruction, the wave simply could not have been found. It had been hiding in plain sight for as long as humans have studied the sky, its individual components studied exhaustively for decades, but its unity invisible because the third dimension was missing. This illustrates the broader challenge of mapping the Orion Arm. The arm is not merely large. It is three-dimensional. It has width, length, and thickness. Its structures rise above and plunge below the galactic midplane. The Radcliffe Wave oscillates vertically through the disk. The arm's gas layer warps slightly as it extends outward from the galactic center, following the known warp of the Milky Way's outer disk. Understanding the arm's true shape requires not just a flat map, but a full volumetric reconstruction, and that reconstruction is still far from complete. Current high-precision mapping covers roughly the nearest 10,000 light-years in most directions. Beyond that, distance uncertainties grow, dust obscuration thickens, and the details begin to blur. The far reaches of the Orion Arm, particularly toward Carina in the southern sky, remain poorly constrained. Maser parallaxes have probed some distant regions, but coverage is uneven. Large areas of the arm's extent rely on velocity-based distance estimates that carry substantial uncertainty. Gaia Data Release 4, expected in 2026, will improve the picture further by incorporating more than 5 years of observations and providing better parallaxes for fainter, more distant stars. But even Gaia has limits. Beyond roughly 15 to 20,000 light-years, parallax angles become too small for Gaia to measure reliably, and the farthest reaches of the arm remain accessible only through radio techniques and model-dependent methods. Now step back and consider the full picture of how the Orion Arm sits within the Milky Way's larger architecture. The galaxy has two confirmed major arms, Perseus and Scutum Centaurus, which dominate the overall spiral pattern. Two additional arms, Sagittarius and Norma, are classified as minor arms, containing strong concentrations of gas and young stars but lower overall stellar density than the major pair. The Orion Arm lies between Sagittarius and Perseus, and its recently upgraded properties place it somewhere in the ambiguous territory between a minor arm and a major one. Some models now describe the Milky Way as having 4 major arms. Others prefer a 2+2 arrangement with 2 dominant arms and 2 or more secondary features. The Orion Arm's classification depends on which model you adopt. The debate over the Milky Way's spiral structure is not resolved. Some researchers, based on analyses of maser distributions and gas kinematics, favor a 4-arm model with fairly symmetric spiral features. Others, incorporating Gaia data and three-dimensional dust maps, argue for a messier picture with less distinct arm-inter-arm contrasts and more substructure. A 2025 study tracing kinematic perturbations in stellar velocities using combined Gaia and spectroscopic data noted that the classification of the local arm as a major arm remains contentious, with some studies describing it as a minor spur and others insisting its properties are comparable to the galaxy's dominant features. What is not in dispute is that the Orion Arm is a real, substantial, physically coherent galactic structure. Whether it earns the formal designation of major arm or remains technically a secondary feature is a question of classification, not reality. The arm exists. It is large. It contains active star formation rivaling anything in its neighbouring arms. It has a measurable pitch angle, a traceable extent, and an internal structure complex enough to contain features like the Radcliffe Wave that span thousands of light-years. From our position inside it, the arm shapes nearly everything we observe. When we look along the galactic plane towards Cygnus, we are looking down the length of the Orion Arm. The dense concentration of stars in that direction, the rich star fields that fill binoculars and wide-field cameras pointed at the Cygnus region, is the arm seen in profile. It's stars and gas piled up along our line of sight over thousands of light years. When we look toward Orion in winter, we are looking roughly perpendicular to the arm's length, across its width, into the dense star-forming complexes that populate the arm's interior. The structure of the arm determines the structure of our sky. We cannot see the arm's spiral curve. That curvature unfolds over tens of thousands of light years, a gentle arc that would require a vantage point far above the galactic plane to appreciate visually. From inside, the arm appears as a band of enhanced stellar density along the galactic plane, thicker in some directions than others, brighter where major star-forming regions concentrate, darker where dust clouds intervene. The spiral structure is inferred, not observed directly. It emerges from thousands of individual distance measurements, each one placing a single star or gas cloud at a specific point in three-dimensional space, until the accumulated points trace out the curve. Assembling this picture is like reconstructing the shape of a mountain range by listening to how sound bounces through its valleys without ever climbing above the tree line. You hear echoes, you time delays, you triangulate directions. Piece by piece a shape emerges, but you never see the peaks. You never see the ridgelines silhouetted against the sky. You work with fragments, always aware that the full picture might look different from what your fragments suggest. This is the state of our knowledge of the Orion Arm. We have mapped its nearby regions in extraordinary detail. We know its width, its approximate length, its pitch angle, and the locations of its major star-forming complexes out to several thousand light years. We have identified its internal substructures, from the Radcliffe Wave to the Cepheus spur, to the great molecular cloud complexes in Orion and Cygnus. We have placed our Sun within the arm at a specific, well-measured location near its inner rim, but the full arm extends far beyond our high-precision mapping. Its distant reaches remain uncertain. Its relationship to the Perseus arm, whether it is truly independent or a branch of the larger feature, is still debated. Its far-end structure, toward Carina and beyond, is constrained more by models than by direct measurements. The Orion Arm is not fully mapped. It is partially mapped. We see the nearby rooms clearly. The distant wings of the building are still sketched in pencil, subject to revision as better data arrives. And that is what makes the arm both a triumph and a humbling reminder. A triumph because the techniques that revealed it, maser parallaxes, space astrometry, three-dimensional dust mapping, radio spectroscopy, represent some of the most precise measurement capabilities humanity has ever developed. We measured the structure of a galactic spiral arm from inside it, starting from a wooden board with 25 nails and cotton balls, and ending with a spacecraft that catalogued 2 billion stars. That is an astonishing accomplishment, and humbling because, after all of that effort, we still cannot see the full thing. We still do not know its complete extent. We still argue about whether to call it a major arm or a minor one. We have lived inside it for 4.5 billion years, and we are still figuring out what it looks like. That unfinished map is itself a statement about scale. The Orion Arm is large enough that a civilization with space telescopes, continent-spanning radio interferometers, and a spacecraft that catalogued 2 billion stars has not yet been able to fully chart the structure it lives inside. The arm exceeds not only our intuition but, in some directions, our current observational reach. And now that we know how it was mapped, and how large it turned out to be, the final question becomes unavoidable. What does it actually mean to live inside something this vast? What does it feel like? Or what should it feel like? To realize that the part of the galaxy you call home is not a small local patch, but a structure large enough to swallow every familiar object in the sky and still stretch on for thousands of light years beyond. Begin with the Sun. A single star, yellow-white, middle-aged, roughly 860,000 miles across, massive enough to hold 1.3 million Earths inside its volume, converting roughly 4 million tons of matter into pure energy every second through nuclear fusion, radiating more energy in a single second than human civilization has consumed in its entire history. By any terrestrial measure, the Sun is overwhelming. It dominates the solar system so completely that it contains 99.86% of all the mass within it. Everything else, all 8 planets, all the moons, all the asteroids and comets and dust, is a rounding error. Now, wrap the solar system around that sun. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, the Kuiper belt beyond Neptune, the scattered disk stretching farther still. And then the Oort cloud, that hypothetical spherical shell of icy bodies extending perhaps 2 light-years from the Sun in every direction, marking the outermost gravitational reach of our star. This is our world, the full extent of everything gravitationally bound to the Sun, a sphere roughly 4 light-years in diameter. It took Voyager 1, launched in 1977 and travelling at about 17 kilometers per second, over 35 years to cross the heliopause and enter interstellar space. And the heliopause sits roughly 120 astronomical units from the Sun. The Oort cloud, if it exists at its theorized extent, is roughly 100,000 astronomical units away. Voyager 1 will not reach the inner edge of the Oort cloud for another 300 years. It will not clear the outer edge for roughly 30,000 years. 30,000 years. That is how long it takes our fastest spacecraft to escape our own solar system. And the solar system, in its entirety, spans roughly 4 light-years. The Orion Arm spans at least 20,000. Place those two numbers side by side. 4 and 20,000. The arm is 5,000 times longer than the full diameter of our solar system. The region of space that contains every planet, every moon, every comet, every asteroid, every spacecraft humanity has ever launched, and every object gravitationally bound to our star occupies 1/5,000th of the arm's length, not its volume, just its length. This is what embedded means. The solar system does not sit beside the Orion Arm. It does not occupy a noticeable fraction of the arm. It exists inside the arm the way a candle flame exists inside a darkened aircraft hangar, present, real, burning steadily, and absolutely invisible against the scale of the structure that surrounds it. Now zoom in even tighter. You are standing on Earth. The planet is 12,756 kilometers in diameter. It orbits the Sun at a distance of about 150 million kilometers. This orbit, the circle your planet traces through space every year, has a diameter of roughly 300 million kilometers. 300 million kilometers sounds immense. It is immense. Light takes about 16 minutes to cross it. But convert that to light years and it becomes roughly 0.000032 light years. Now, compare that to the arm. The arm is 3,500 light years wide. Earth's orbit around the Sun is about 109 million times smaller than the arm's width. Your planet's annual path through space, the circle that defines your seasons and your calendar, and your entire experience of solar astronomy, is 109 million times smaller than the width of the galactic structure you live inside. You cannot visualize that. No human can. The ratio between your orbit and the arm's width is roughly the same as the ratio between a single human red blood cell and the length of a football field. Your entire yearly journey around the Sun, the path that carries you through summer and winter, through the longest days and the shortest nights, is a blood cell on a football field. And the football field is only the arm's width. Its length is another 6 times farther. This is not abstract. This is geometry. This is the real physical relationship between the space you move through and the structure that contains you. And the structure is not far away. It is here. It is the medium you exist within. It starts at the edge of the local bubble and stretches thousands of light years in every direction, filled with gas and dust and stars and nebulae, and the remnants of stellar explosions that happened before our planet formed. Consider what it means for light. A photon leaving the Sun right now, travelling at the fastest speed the universe permits, will take 4 years to reach the nearest neighbouring star. It will take roughly 1,000 years to cross the local bubble. It will take 3,500 years to cross the arm's width, and it will take at least 20,000 years to travel the arm's full length. 20,000 years. When the last photon from the Sun that will reach the far end of the Orion Arm finally arrives there, it will have been travelling since before the end of the last ice age. It will have left the Sun when woolly mammoths still walked the Earth, when human beings were painting caves in southern Europe, when agriculture had not yet been invented. By the time that photon reaches the far end of the arm, entire civilizations will have risen and fallen without it ever arriving. And that photon was traveling at the speed of light the entire time. Nothing in the universe could have carried information faster. This means the Orion Arm is not just spatially vast, it is temporally vast. The structure is so large that the speed of light, the absolute cosmic speed limit, cannot cross it within the span of recorded human history. Even light is slow inside the arm. Even the universe's fastest messenger takes thousands of years to traverse the structure that contains our sun. If you sent a radio signal from Earth right now, aimed directly along the arm's length, and a civilization at the far end were listening, they would receive your message 20,000 years from now. Their reply would arrive 40,000 years after that. A single round-trip conversation would take longer than the entire history of human civilization to date. This is what it means to be embedded. Not merely that the arm is large, but that it is large enough to impose isolation even at the speed of light. The different regions of the Orion Arm are causally disconnected from each other on human timescales. A supernova exploding at one end of the arm right now will not be visible from the other end for 20,000 years. Stars forming in the Cygnus X complex are creating light that will not reach the Carina end of the arm until civilizations that do not yet exist have time to rise and fall. The arm is a single structure, but it is not a single moment. It is a structure so large that different parts of it exist in different observational epochs simultaneously. When we look along the arm towards Cygnus and see stars 4,000 light-years away, we are seeing those stars as they were 4,000 years ago. When we look toward the Orion Nebula at 1,340 light-years, we see it as it appeared when the early Middle Ages were reshaping Europe. Each direction we look within the arm is a different depth of time. The arm is not just a place. It is a temporal landscape, a structure that encodes thousands of years of history in the light that reaches us from its various regions, and we sit near the middle of it, not at a special vantage point, not at a center, not at a boundary, just somewhere in the arm's midsection, on the inner rim, tucked inside a small bubble of cleared-out gas, orbiting an unremarkable star on an unremarkable planet, looking out into a structure that extends farther than we can see, farther than our light has travelled, farther than any message we have ever sent could reach in a human lifetime, and we are not even permanent residents. This is the part that rarely gets said. The Orion Arm is not our eternal home, it is our current home. As we discussed, density wave theory tells us that spiral arms are patterns, not fixed containers. Stars and gas drift through them over millions of years, entering on one side, spending time inside, and eventually exiting on the other. Our Sun is doing exactly that. It orbits the galactic center at roughly 720,000 kilometers per hour, tracing a vast circle that carries it through different regions of the disk over hundreds of millions of years. Right now, that orbit places us inside the Orion Arm, but it has not always been so, and it will not always remain so. In roughly 100 million years, give or take, the solar system will likely have drifted out of the arm and into the lower density interarm space between the Orion Arm and the next structure along. The stars currently surrounding us, the familiar constellations, the nearby stellar nurseries, the Radcliffe Wave rippling through the arm's interior, all of it will still exist, but we will no longer be inside it. We will have moved on. New stars, born from gas clouds that have not yet collapsed, will populate the arm in our place. Other planetary systems, many of them not yet formed, will take up residence in the same stretch of galactic structure that we currently call home. The arm endures. Its residents rotate through. We are seasonal visitors in a landscape that persists long after any individual inhabitant leaves. The Orion Arm existed billions of years before our Sun was born, and it will exist billions of years after our Sun burns out and fades to a cold white dwarf drifting through whatever part of the galaxy its orbit has carried it to by then. Our time inside the arm, the entire 4.5 billion year lifetime of the solar system so far, is one brief passage through a structure that operates on timescales far longer than any single star's life. We are not anchored here. We are passing through, and the arm barely notices. This is the final dimension of being lost. We are not just small inside the arm, we are temporary inside it. The structure that contains us will outlast our star, will outlast every trace of the solar system's existence within it. And when we are gone, the arm will continue forming stars, building nebulae, oscillating its Radcliffe Wave up and down through the galactic plane, indifferent to the fact that one unremarkable yellow star once drifted through its interior, carrying a small blue planet where something briefly looked up and wondered what it was all part of. Now flip the perspective entirely. Imagine you are not inside the arm. Imagine you are far away, looking back at it. Picture yourself standing on a planet orbiting a star in the Andromeda Galaxy, 2.5 million light-years away. You have a telescope powerful enough to resolve individual features in the Milky Way's disk. What would you see? You would see a spiral galaxy, roughly edge-on from Andromeda's vantage point, with luminous arms winding through a flattened disk of stars. The Orion Arm would appear as one faint streak of concentrated light among several, a modest spiral feature nestled between the brighter Perseus Arm outward and the Sagittarius Arm inward. It would not stand out. It would not be labelled. It would be one structural thread in a complex weave of galactic architecture, visible primarily because of the bright young O-type and B-type stars tracing its length, and our Sun. It would be invisible, completely, utterly invisible. A single G-type star among billions, far too faint for any conceivable telescope at that distance to resolve individually. The local bubble surrounding it would be undetectable. A 1,000 light-year cavity in the interstellar medium is a microscopic feature at the scale of a full galaxy, seen from millions of light-years away. The solar system, with all its planets and moons and spacecraft, and the sum total of human ambition, would not register in any observation an Andromedan astronomer could ever make. We would be lost inside the arm, not only from our own perspective looking out, but from every external perspective looking in. The Orion Arm itself would be merely one visible feature among many in a galaxy that, from Andromeda's distance, spans less than a few degrees of sky, and inside that feature we would be nothing. Not hidden, not obscured, simply too small to exist at that resolution. This is what lost means from both directions. From inside, we cannot see the arm's edges. From outside, no one could see us within it. This is the nesting that makes the arm so disorienting. Start with the solar system, a 4 light-year sphere. Inside that sphere, the Sun and its planets, everything humanity has ever physically touched. The solar system sits inside the local bubble, a cavity roughly 1,000 light-years across. The bubble is the solar system's immediate interstellar environment, a region of hot, thin gas carved by ancient supernovae. It contains most of the stars visible to the naked eye. It is the volume of space that feels, from a human perspective, like the local neighborhood. The local bubble sits inside the Orion Arm. The arm is at least 20,000 light-years long and 3,500 light-years wide. It dwarfs the local bubble the way a river dwarfs a puddle. The bubble is a small pocket within the arm's interior, one cavity among many, surrounded by denser gas and molecular clouds and star-forming regions that extend in every direction for thousands of light-years beyond the bubble's walls. The Orion Arm sits inside the Milky Way. The galaxy spans roughly 100,000 light-years across and contains hundreds of billions of stars distributed across multiple spiral arms, a central bar, a bulge, a thin disk, a thick disk, and an enormous dark matter halo extending far beyond the visible structure. The Milky Way sits inside the local group. The local group sits inside the Virgo supercluster. The Virgo supercluster sits inside the La-Niña-Gaia supercluster. And La-Niña-Gaia is one structure among countless others in the observable universe, which spans 93 billion light-years and contains approximately 2 trillion galaxies. Each layer in this hierarchy is staggeringly larger than the one before it, but the step that most people skip, the step that this entire story has been about, is the one between the solar system and the Milky Way, the Orion Arm, the structure that fills that gap, the thing that most cosmic address lists simply leave out, jumping from our Sun to our galaxy as if there were nothing meaningful in between. There is something meaningful in between. There is a spiral arm 20,000 light-years long that contains billions of stars, active stellar nurseries, a 9,000 light-year oscillating wave of gas and newborn stars, and enough molecular material to keep forming new stellar systems for millions of years. And our solar system is a speck buried so deeply inside it that it takes light thousands of years to escape the arm's boundaries in any direction. This is not a metaphor. It is not poetic exaggeration. It is the literal, measured, scientifically confirmed geometry of where you exist. And this is where the deeper realization arrives, the one that changes how the arm feels. When people talk about feeling small in the universe, they usually mean something distant. They mean the billions of light years separating us from the edge of the observable cosmos. They mean the 2 trillion galaxies scattered across that expanse. They mean the abstract, faraway vastness that exists out there, beyond everything familiar, in regions so remote that they require telescopes and mathematical models to even conceptualize. But the Orion Arm is not out there. It is in here. It is the local structure. It is the part of the galaxy that contains every star you have ever seen, every constellation you have ever named, every object you have ever pointed a backyard telescope at. It is not the distant universe making you small. It is your own neighborhood, the part of the galaxy that feels closest, most familiar, most intimate, is already large enough to make the solar system effectively invisible within it. This is the collapse that the title promises, not the vastness of deep space, not the unimaginable distances between galaxies. The true shock is that even the local region, the part of the Milky Way you casually call home, is already so large that the solar system feels lost inside it. You do not need to travel to the edge of the observable universe to confront the irrelevance of human scale. You just need to look carefully at the arm you are already in. Think of it like this. Imagine someone born inside a single room. They know the room well, its walls, its furniture, the view from its one small window. They are told the room is part of a building. They imagine the building is slightly larger than the room, maybe a dozen rooms total, manageable, comprehensible, a place they could walk through in an afternoon. Then one day they open the door and discover the building has no visible end. Corridors stretch in every direction. Other rooms branch off by the thousands. Entire wings extend beyond sight. The building is so large that a person walking at a steady pace could not traverse it in a lifetime. The room they knew, the one they called home, is not a significant fraction of the building. It is one room among millions, indistinguishable from any other, tucked into a corner of a wing they cannot see the end of. That is the Orion Arm. The building you just discovered is not the galaxy. It is not the universe. It is just the arm, just the local feature. The room is the solar system. The building is the structure that contains it. And the building is so large that it breaks the assumption you never knew you were making, the assumption that home is small. We carry that assumption unconsciously. Humans compress geography. We flatten distances. We simplify nested structures into manageable labels. We say we live in the Milky Way and skip the arm entirely, as if the step from our sun to the full galaxy is one clean jump. It is not. Between our sun and the galaxy lies a structure 5,000 times longer than our solar system, containing billions of other stars, each one as real and as burning as our own, most of them completely unknown to us, many of them surrounded by their own planets and moons, and possibly their own versions of pale blue dots where something might be looking up at a sky full of other arm-resident stars, and feeling exactly the same thing we feel when we look up and assume the sky belongs to us. It does not belong to us. The sky belongs to the arm. Every star in it is a fellow resident of the same galactic structure, and most of them are so far away that their light takes centuries or millennia to reach us. We share a home with billions of stars and we will never visit any of them. We will never send a message that arrives at the arm's far end within a human civilization's lifespan. We are neighbors in name only, connected by structure, separated by scale. This is the paradox of the Orion Arm. It is home. It is genuinely, physically, structurally the galactic environment that contains our sun and our planet and everything we have ever known. But it is a home so large that the word loses its meaning. Home implies familiarity. It implies a space you can know, can navigate, can hold in your mind as a complete picture. The Orion Arm defeats all of that. It is a home you cannot see the edges of, a home you cannot cross in 100,000 lifetimes, a home that contains more stars than you could count if you spent every second of your life doing nothing else. And this brings us to the final, most unsettling layer. The Orion Arm is not even a large structure by galactic standards. The Perseus Arm, which lies just outward from us, stretches more than 60,000 light-years along its arc. The Scutum Centaurus Arm wraps even farther around the galaxy's interior. The full Milky Way disk, with all its arms and interarm regions, spans 100,000 light-years or more. The Orion Arm, at 20 to 25,000 light-years, is one of the smaller spiral features in the galaxy. This means the structure that already makes our solar system feel invisible is itself a modest feature within a much larger system. The arm that dwarfs everything we know is dwarfed in turn by the galaxy that contains it, and the galaxy is dwarfed by the local group, and the local group is dwarfed by the supercluster. The hierarchy of scale does not stop. It keeps climbing, and at every level the structures below shrink into insignificance. But there is something specific about the Orion Arm that makes its scale feel different from the abstract vastness of galaxy clusters and superclusters. Those larger structures are far away. They are out there, beyond the reach of any personal connection. The Orion Arm is not out there. It is the thing you are inside of right now. It is the immediate galactic environment. The gap between you and the arm is zero. You are part of it. Your atoms were forged in stars that lived and died within it. The iron in your blood was manufactured in a supernova that exploded somewhere inside this arm billions of years ago. The calcium in your bones came from a dying star that shed its outer layers into the arm's interstellar medium. You are not observing the arm from outside. You are made of it, and yet you cannot feel it. You cannot sense its boundaries. You cannot perceive its shape. It is too large, too surrounding, too encompassing to register in ordinary awareness. It is the ultimate invisible environment, a structure vast enough to contain billions of stars, and yet subtle enough that a species living inside it can go its entire history without knowing it is there. Astronomers discovered the Orion Arm less than a century ago. For the vast majority of human existence, no one on Earth knew that the stars in the sky traced a specific galactic structure. No one knew that our sun sat near the inner rim of a spiral arm. No one knew that the bright band of the Milky Way was a disk of stars seen from inside, let alone that within that disk, our local region constituted a defined, measurable, nameable piece of spiral architecture. We found it. We mapped it. We measured its dimensions. We upgraded it from a minor spur to a legitimate arm segment. We discovered that it contains a 9,000 light-year oscillating wave of gas and newborn stars running through its interior like a backbone. We placed our sun within it at a specific, well-determined location. We traced its connections to the neighbouring arms and fit it into the larger pattern of the Milky Way's spiral structure. And after all of that, the most striking fact remains the simplest one. The Orion Arm is the part of the Milky Way that we call home. It is not the whole galaxy. It is not even one of the galaxy's most prominent features. It is our local arm, our immediate galactic neighbourhood, the thing between us and the larger galaxy. And it is already, by itself, without invoking anything beyond it, so large that our solar system vanishes inside it. You do not need to zoom out to the observable universe to feel the weight of cosmic scale pressing down on human significance. You do not need to invoke 2 trillion galaxies or 93 billion light-years. You just need to understand what it means to live inside a single spiral arm of a single galaxy. A structure 20,000 light-years long, 3,500 light-years wide, containing billions of stars you will never see, and distances you will never cross, stretching in every direction far beyond the reach of your fastest light, your strongest signal, your most ambitious imagination. The Orion Arm is home, and home is so much larger than we ever thought that the word barely applies anymore. Not because the universe is vast, although it is, but because even the local part of it, even the piece we casually label ours on a diagram, is already vast enough to make us almost anonymous inside it. That is the true scale of the Orion Arm, not a label on a map, not a footnote beneath a galaxy illustration. A real, physical galactic structure large enough to hold everything humanity has ever known and still stretch on for thousands of light years beyond, filled with stars and gas and light we will never reach. A structure large enough to make the solar system feel lost inside the part of the galaxy we call home. Every star you have ever wished upon burns somewhere inside it. Every constellation you have ever traced lives within its borders, and it extends so far beyond those familiar lights that even at the speed of light, you would need 20,000 years to see it all. We are inside the Orion Arm. We have always been inside it, and now, for the first time, we are beginning to understand just how deeply buried we really are.